Okay, so this is going to be my third and final lecture. And so I'd like to talk about some new approaches to the Hart-Simon theory. And briefly at the end, I probably won't have time to really explain how it applies to mean curvature flow. But I want to talk about a new approach to the Hart-Simon theory, which still has the similar sort of perturbation to one side, is looking at how the singularities behave, but it avoids the classification of the foliation. Okay, and so the motivation for this really comes in from mean curvature flow, but I want to talk about it in the minimal surface setting. Okay, so this is going to be joint work with Kyung-Soo Choi, Christos Mantelidis, and Felix Schulze. Okay. And so the main outcome of this lecture is going to be sort of a softer proof of the Hart-Simon theorem, because you don't need this pretty difficult classification of the foliation. And so what I want to talk about is the following proposition. So there's some number, delta bigger than 0. It's just a numerical constant. And so suppose you have an area minimizing mean cone. It's non-flat. Okay, so of course the hyperplane is area minimizing, but I don't want to consider that. And then okay, so suppose you have an area minimizing surface that doesn't cross the cone. So but you can just imagine that it lies on one side of the cone, right? Then, so for any point that's not the origin, you have the following density drop. Okay, so if you remember, in some sense, this result is kind of vacuous, right? Because we've seen that if you have an area minimizing cone in R8, well, it's regular. So then you can apply Hart-Simon. And then you know that for a regular cone, if you have an area minimizing surface on one side of a regular cone, then you must be completely smooth. So that's the Hart-Simon foliation result. So in particular, right, on the other hand, we know that this is definitely bigger than 1. That's by Allard. And this is then equal to 1 because it has to be smooth. So this proposition is, if you want to use the Hart-Simon theory, completely trivial. But what I want to point out is that you can give a simple proof of this proposition, which is weaker than the Hart-Simon theory, but this actually is going to be sufficient to prove the generic regularity. Okay, so let's prove this. Okay, so the first step is reduce to delta equals 0. And so what I want to do is I'll just use a compactness argument. So the set of area minimizing cones in R8 is compact. And so you can take the limit of area minimizing cones and then get another area minimizing cone. It's still regular. So the limit is very nice and smooth. And so if we had a sequence of counterexamples where this delta was going to 0, so counterexamples violating the statement with smaller and smaller delta, we could always choose these points. Everything is dilation invariant. So we could assume that these points have a distance 1 from the origin, and we could pass the limit, right? So in other words, what we get is that there exists a cone and a surface so you get an area minimizing cone and an area minimizing surface that doesn't cross the cone, and a point x naught, which is not the origin. We scaled it to have distance 1, but it doesn't matter. The density of sigma at the point x naught is at least the density of the cone. Okay, so this is essentially what you get out of just a contradiction argument. And so you use the contradiction to squeeze a little bit of room out of just a statement like this. Okay, So we want to show that this is a contradiction. All right. So the first step, let me draw a picture. So here's the cone C. This is a cone C, and we have this minimal surface sigma on one side of the cone. We have a point x naught, where the density is at least the density of the cone. And so the first step is to consider any tangent cone to sigma at infinity. Okay, so I haven't talked about this in the previous lectures, but this just means instead of zooming in, which is the normal way you construct tangent cones, because sigma is an entire minimal surface, you can also zoom down, like blow down, and look at the behavior of sigma as the radius gets very large. Using the error minimizing property, you can prove that there is some tangent cone C prime. And also you can see, because if sigma and C don't cross each other, then the tangent cones, well, they might touch, in which case they have to agree, but they can't cross, right? So they can't cross. If they touch, then they're equal by the strong maximum principle, but they can't be disjoint, right? And so this can't be disjointness follows from what's called the Frankel property. Sorry, I can't spell Frankel. So, okay, so two minimal surfaces in a 7 must intersect. Okay, so we now see that the cone at infinity of sigma is equal to the cone C that we started with. But now let's think about the monotonicity formula carefully. So if you start at this point x naught, then you start considering a ball of some size. As r goes to infinity, well, sigma at very large scales looks like its tangent cone at infinity. So the density ratio of sigma for very large scales looks like C prime, the density of C prime, but this is exactly the density of C. On the other hand, right, this is bigger than or equal to theta of C, and this is by assumption, right? Because this is this thing. Okay. So, right, I'll just remind you what we're trying to prove. We're trying to show that if you have sigma on one side, then there is a density drop. Okay. And so, okay, so we've reduced to instead of saying a definite density drop, we're trying to show that there's a density drop at all, right? That's this contradiction argument. And then we've considered the monotonicity formula between the point where there's a high density point and infinity. And we've argued that there was no density drop. Okay. So let's see what happens. So we have this, then again, we've ended up with the density of C. So what happens is this must be an equality. Okay, so as we take larger and larger balls around x naught, then the density of sigma cannot change. So, as we've seen, this implies that sigma, not just C, has to be a cone. Okay, so let me adjust the picture. Okay, so sigma is a cone, but if you think about it, well, when we rescaled, if you rescale a cone, it doesn't do anything. So rescaling the cone, we found that sigma converged to C prime. But that means that sigma, if it started as a cone and you rescale it, you get C prime. It has to be equal to C prime, but C prime is equal to C. Okay, so let's be a little bit more precise here. And actually, sigma is C plus x naught. Okay, so everything I said in a moment ago was precisely okay if we translated x naught to the origin and then did this rescaling. So unwinding all that is that if we untranslate x naught, then sigma is c shifted by x naught. Okay, so now, well, this picture I claim is a contradiction. Okay, and so that's going to be the result of the following geometric lemma. Okay, so if you have a non-flat regular hypercone, then translating it by some vector, it must cross the original cone, okay, for any vector that's non-zero. Okay, so let me prove this. Okay, so if translating by x naught doesn't cross, then I could dilate this entire picture where nothing crosses by lambda. And so because C is dilation invariant around the origin, this only has the effect of changing the point that I'm working with, x naught. So that's like moving x naught into the origin. Okay. So I have C, then I take a very tiny translation. So this is C plus lambda x naught. And so the idea is to send lambda to 0. And so as usual, we expect that when you have two surfaces converging to each other, you end up with a Jacobi field. And you get the x naught nu C. So this is the resulting Jacobi field. So, well, you see that this Jacobi field doesn't change sign because it came from one-sided convergence. Okay. So it can't hold okay. So it can't happen that x naught dot nu C is always 0, because you can show that this would imply that C split a line in the x naught direction. So we have this Jacobi field, it doesn't change sign, and it satisfies some elliptic BD, so therefore let's assume that it's positive. But at this point, we're basically done, because this means that C is a graph. Okay, so normally if you have such a function, which is, if you have a vector, constant vector dot the normal, then it's a multigraph, right? But in this case, you can't have two connected components because it's area minimizing. And so now we're done, because, well, there's a variety of ways of concluding here, but graph, a graph that's a minimal surface can't have isolated singularities, right? So you can't have an isolated singularity of a graphical minimal surface. Of course, we've seen that for a non-graphical minimal surface, there's these cones which have isolated singularities, but it can't happen in this case. Okay, so that proves the lemma. Okay, so using this result, I want to explain how you can prove the generic regularity result. Okay. So let me just, so now this is new approach. So again, as before, now let me use the dots. Okay. We have okay, so we're going to consider an area minimizing solution in the ball. So some solution to Plateau's problem with boundary gamma. And what I'm going to do is I first want to foliate a neighborhood of gamma. Oh. Okay, and I should say that sigma has the singular set, the origin. Okay. So I want to consider a whole foliation by 6 manifolds. This is gamma S. Okay, so I'm just moving this boundary up and down. Then for each gamma S, I want to look at the set sigma S solving Plateau for gamma S. And so, okay, the solution to the Plateau problem may not be unique, but it turns out it's very easy to deal with that. So I don't want to worry about that. So let's just say the solution is going to be unique. And so I'm going to define a quantity. So for S close to 0, S is going to be parameterizing my foliation. And so I want to look at points sufficiently close to the origin. And for that boundary data, solve the Plateau problem to get sigma S. And I want to look at the highest density singular point. Okay. And so this is a sort of a numerical invariant of S. And this tells me a lot, right? Because if d of S is equal to 1 for S approximately 0, right? So if I can do a small perturbation, find S so that d of S is 1, then by Allard, right, for that S, sigma S is regular. Okay, so if S is sufficiently small, essentially you can show that the only thing that really could be going wrong is exactly at the near the origin, right? Nothing in between. Okay. And so what I want to do is prove a sort of a non-trivial fact about ds, and that's the following. But I mean, the proof will be easy because it's just essentially reformulating our previous theorem. Okay, so this delta is from okay, so the previous thing I proved says that on one side of a cone, the density has to drop in a non-trivial way. And so the lemma that I want to prove here is that, well, as you limit to S naught, the density always is going to drop by at least delta. Okay, so this implies there exists S approximately 0 such that d of S is equal to 1. Okay, and so strictly speaking, this should say, the max this comma 1. Okay. Okay. So I don't want to claim it goes below 1 because that wouldn't make any sense. So what I do is if I, here's S, here, this is the graph of D. Well, I should start at 0. Then I come in, and whatever D of 0 is here. Then I know that I must be able to go down approximately delta by a small perturbation to one side, right? So this, I've decreased the D by delta, but now I start over at this some S1, and I come in from some side. But if I use this lemma where points are limiting to S1, then again, I must decrease by some amount delta. And I just do this finitely many times, and I've won. I found something where D has dropped below 1. Okay. So let me prove the lemma. Okay, so let's assume that there's some sequence along which this fails. And then, choose xj such that, so, for this sj, I solve the plateau problem. So let's just look back here. So for sj limiting to s naught, I solve the plateau problem. I have this sigma s. Then by assumption, there's some point with large density. Okay. Okay, so I can assume that the limit of these points has the limit of the density of these points is strictly larger than d of s naught minus delta. Okay, so as long as so I did this localization with the ball of 1/2, but as long as s is sufficiently small, that's not a problem. So I can find, I can pass to a subsequence that xj converges to x naught, in the ball of radius 1/2. And so this x naught by Allard will be in the singular set of sigma naught, right? Because, at least ignoring some technicalities, we have these surfaces Sj are looking like this is sigma Sj, here's Xj, and they're converging to some X naught. And remember that singularities converge to singularities, right? So the limit of these Xj's must still be a singular point. But now, what I want to do is I want to rescale by the distance from xj to x naught. So I zoom in. And so when I do this, well, the sigma sj will converge to some sigma tilde, area min hypersurface. The rescalings of xj will converge to some x tilde. And this is going to be a singular point, sigma tilde, and the density of sigma tilde at x tilde, well, the density is going to be at least the limit of theta sigma sj xj. This is by upper semi-continuity of density. Okay, but then this is bigger than d of s naught minus delta by assumption. On the other hand, the rescalings of sigma s naught, these converge to some cone, which is a tangent cone, to sigma s naught at x naught. Okay, and so now you maybe see where we're going. So you have a tangent cone with an area minimizing surface on one side with a high density singular point. And we know that the density of the tangent cone is equal to theta of sigma s naught at x naught, because we saw that the density of the tangent cone is precisely the density of the surface at the point. And this is no bigger than d of s naught, because d of s naught was the highest density singularity. Okay, so let's put this all together. So the density drop proposition, density drop prop, tells us that the density of sigma tilde at x tilde. So, we have our, in the limit, we have our cone, we have our singular sigma tilde, we have x tilde. This is going to be less than or equal to the density of the cone minus delta. Okay, but now using this is less than or equal to the d of s naught minus delta. But using this is bigger than d of s naught minus delta, right? And this is a contradiction, right? That finishes the proof. Of course, if you're worried about the less than equal to, it seems like we barely squeaked by. But of course, you could have given yourself a little bit of room, and that also would have made things work okay. All right. So just to recap, what we did is we used this density drop proposition, right? So if you're a area minimizing surface not crossing a cone, lying on one side of the cone, then your density drops by a definite amount at any point, right? So even though we know by work of Hart Simon that there's really no singular points, here we can say that there, at least the density has to drop by a definite amount. And then we use this to repeatedly perturb the density down at the highest density point. Okay, so this sort of result proves the plateau version of Hart and Simon, but you could also use it to talk about the Smale version in homology. Okay, so I'll briefly just mention some related work in mean curvature flow by myself, Choi, Mantelides, and Schulze. And so essentially the idea, and don't want to get too into the details, is that mean curvature flow, so this is the flow right? So it's a family of hypersurfaces flowing in the direction of the mean curvature vector. And so the key observation is that, well, mean curvature flows acts a lot like minimal surfaces. It has a monotonicity formula due to Huisken, and it has singularities in mean curvature flow. The singularities, you could call them tangent flows. And so in this setting, you might worry that mean curvature flow minimal. Okay, so mean curvature flow is the gradient flow of the area functional, but you might kind of imagine that should be related to critical points of the area functional. And indeed, in many senses, that's true. But when it comes to talking about the generic behavior of mean curvature flow, it turns out that actually it behaves a whole lot like the area minimizing setting. And so the key point is that what do you get when you're area minimizing? Well, in that version of the problem, you can always minimize area, right? And so for minimal surfaces, oftentimes you can't perturb and construct a nearby one because you don't have a way of minimizing, right? So the minimizer might be very far away, so you can't use arguments based on minimization in a lot of settings. But for mean curvature flow, you can perturb slightly and flow, right? So that's sort of the analog of area minimizing. And so I'll just briefly discuss the results. Okay, so remember in mean curvature flow, there's, instead of tangent cones, you have tangent flows. So you have to use a different sort of scaling because it's a parabolic problem. And so for the experts, certain means compact, asymptotically conical shrinkers. Right, so tangent flows, instead of being cones, are the support of a self-shrinker. Okay, and so when those shrinkers have certain behavior at infinity, what you could do is the parabolic analog of the Hart-Simon foliation exists, is unique, and has desirable properties. Okay, and so just in a picture, so this might be some tangent flow. And in this tangent flow, perhaps it's a kind of an undesirable singularity. And so what we proved is that the correct way of thinking about this is you should look in the complement of the space-time track of the tangent flow, and there exists ancient solutions to mean curvature flow are like entire minimal surfaces, just like the Hart-Simon theory produces entire minimal surfaces on one side of a cone. There exists ancient mean curvature flows with nice properties. So okay, and so once you sort of see in what direction you should be going, this you actually turns out that the proof is quite similar to Hart and Simon, with the complication that you end up needing to consider a class of shrinkers which is more general than just compact shrinkers, which is sort of the analog of regular cones. And it seems likely that this result should extend to more general sets of shrinkers, but that's work in progress. And so let me just say, so if you have an embedded surface in R3, you can perturb it slightly and flow by mean curvature flow so that the flow only has spherical and cylindrical singularities up to a certain time. And so spherical and cylindrical singularities are, well, for various reasons, these should be thought of as the generic singularities in this problem. And so if you flow up until time t, one of two things happen. Well, I guess there's three things. So mt is empty. So the flow goes extinct. So if you have a sphere, right? So the mean curvature flow of a sphere disappears at some time. Okay, so one possibility is the flow only has spherical and cylindrical singularities after doing this initial perturbation, and it flows nicely until it goes away. Multiplicity. Okay, so multiplicity could occur, and this is a major open problem in mean curvature flow in general. You might dream that it doesn't occur in R3, or maybe it doesn't occur generically, but both of those questions I think are quite well, completely open. And then the final thing that could occur, I'll just draw the picture. So there's some weird shrinker with a cylindrical end. And so this case is conjecturally just can't happen, but that's not known. And it seems likely that actually this case can be perturbed away. So that's work in progress. So I think it's likely that that case isn't going to occur generically. It's not clear if it should occur at all. And so essentially what this does is it says that the only thing that could happen for a generic flow is multiplicity. And of course, that's a really big only. And so that's not very desirable, but still it at least reduces the case to sort of the one last remaining thing that could happen in this setting. And so the this result and this Hart-Simon result, you really need this full classification of flows on one side of shrinkers, particularly because in this result, you have to use right. So it's a little bit technical, but this result, you have to localize at the first singular time, because if you don't work at the first singular time, really crazy things could happen later on, and you don't quite know what to do. But in certain settings, in some sense, in settings where multiplicity is automatically ruled out, and in other and a few other things, it turns out that you can use the analog of what I described as the sort of the second approach to Hart-Simon and construct in the low entropy setting. And so entropy is the Gaussian area over all scales. And so it was introduced by Colding-Minicozzi. And so I should say that when Colding-Minicozzi introduced entropy, they used it to prove linear classification. So they used it to prove classification of linearly entropy stable singularities. And this is spheres and cylinders. And so in particular, entropy stable singularities are precisely spheres and cylinders, and that's exactly what is seeing in these generic flows. So there's a big relation, which I don't think I have time to discuss. But let me just briefly close by saying the following. Okay, so start with a surface in R3, which has entropy. So this is the Gaussian area over all scales, less than or equal to 2. So in essentially, you can think that a multiplicity 2 plane, right? So multiplicity 2 plane has entropy equal to 2. So this is kind of already ruling out 2 planes coming together. And then if you have such an object, then after up to a small perturbation, the mean curvature flow has only sphere cylindrical singularities. Okay. And then similarly in R4, so there's some tiny number, epsilon naught, so that if you're below the generalized cylinder, you might call this the bubble tree, S1 cross R2, then small. Right? So if you have embedded 3 manifold in R4 with entropy below this bubble sheet plus a little bit actually, then you can perturb it slightly, and the mean curvature flow only has spherical and cylindrical singularities. Okay, so what I'll close this talk by doing is talking about a few applications. So this particularly, I'll talk about this second result. And so this result has a few applications. In particular, first, it gives a new proof of a result of Bernstein and Wang, Jacob Bernstein and Liu Wang, who proved this using a different method, related but different. Oh, I didn't state the corollary. So M3 in R4, lambda of M less than or equal to lambda of S2 cross R, right? And so this is more restrictive than this statement, right? So the S2 cross R has smaller entropy than the bubble sheet, and so this is a smaller set of M's. Then M is isotopic to S3, so the round sphere, right? So this is, you could call this a low entropy Schoenflies theorem. Okay, so the Schoenflies conjecture says that if you have any M homeomorphic to S as 3 embedded in R4, then it's isotopic to the round S3. So this says, well, you don't even need the homeomorphic assumption if you include a very low entropy assumption. And so what we can do is give a new proof using mean curvature flow. So Bernstein and Wang also used mean curvature flow, but in a different way. So to do a slight perturbation and apply the theorem. Okay, so exists MT, MCF with only spherical and cylindrical singularities. But cylindrical singularities cannot happen by the entropy assumption. So what you find is that there's some M, you perturb it slightly to M prime, right? This is a completely isotopic maneuver. And then M prime flows under mean curvature flow, and it disappears in a round point, right? So it disappears at some time, but if you zoom in, it looks basically like a round sphere. So what this does is the mean curvature flow is providing the isotopy to the round sphere. Okay. And so based on the sort of the strengthening of this, we've conjectured that we've conjectured that you can weaken the entropy assumption. And I think this should be achievable. And so one of Felix's students is in the process of checking some proof of this. So I think hopefully within a short amount of time, it will be a theorem, but we're still not 100% sure. But the idea is that in this setting, you cannot rule out cylindrical singularities. And so instead, you need to sort of construct an isotopy out of some sort of sorted procedure. And there's some provenance for doing such a thing. This has been done in other settings in the past. Okay, so I will stop my talks there, and thank you for anyone who has made it this far through my lectures, and hope to see you in person sometime.